Okay. So have you ever had like that feeling where you really want to understand something like really fundamental to, the way the universe works, but you just don't have the time to do all the research?
Oh, absolutely.
You know what I mean? Like you're so curious about it, but it's like, where do you even begin?
Yeah, you just want to get to the core of it without having to read, thousands of pages.
Exactly. So that's kind of what we do here. And we've had a ton of questions about this one. So we did a deep dive into Higgs Boson. Das Teilchen hinter der Massneuträgung.
Okay, cool.
To pull out the good stuff, the really key insights.
The essence of the Higgs boson.
Yeah, so we're focusing on this Higgs boson, and the core idea, at least from what we've read in this book, is it's a fundamental particle in the standard model.
Right.
And like the standard model is kind of our current, best understanding of the universe at like the smallest scales, right?
Yeah. The best theory we have right now to describe the universe.
Yeah, so the Higgs boson is like this little excitation in something called the Higgs field.
Right.
And it's responsible for giving other fundamental particles their mass.
It is.
Okay, so mass, like it's so basic to everything, right?
It's something we experience every day.
We take it for granted.
Yeah.
But the idea that it comes from this field and this particle, it's pretty wild, right?
It is mind-blowing if you think about it.
It really is. So, like we discussed, your goal today is to, make sure everyone understands, like, why the Higgs boson is such a key player in quantum physics.
Right.
And what its potential might be, for the future.
Yeah.
Maybe even some technologies, without getting too bogged down in the weeds.
Right. Like, what are the implications of the Higgs boson for quantum physics and technologies without, going too deep into the technical details?
Exactly. Just the essence.
The essence.
Yeah. So where did this whole idea come from?
Yeah.
The Higgs boson wasn't always like this well-known part of science, was it?
No, not at all, actually.
Right.
The concept was proposed in 1964 by several physicists, including Peter Higgs, Francois Englert, and Robert Brout.
Okay.
And their idea was groundbreaking because it was an attempt to explain why certain particles, specifically the W and Z bosons, which are responsible for the weak force, have mass.
Okay, so if it was predicted that long ago, why did it take so many years to actually find it?
Yeah, well, that's the real challenge with the Higgs boson.
Okay.
Is that in order to detect it, you need massive amounts of energy.
Okay.
And we're talking about the kind of energy that you only get when you smash particles together at nearly the speed of light.
Yeah, I can imagine.
And for decades, we simply didn't have the technology to do that.
Right.
We didn't have machines powerful enough.
So this is where the LHC comes in.
Exactly, the Large Hadron Collider at CERN.
At CERN, right.
Yeah.
So that was finally the machine that could reach those energy levels.
Exactly. The LHC can create collisions at energies measured in tera-electron volts, or TeV.
Tera-electron volts, wow.
And that's the kind of energy that you need to have a chance of detecting the Higgs boson.
Okay, and so then that finally happened, right?
Yeah. So on July 4th, 2012, the ATLAS and CMS experiments at CERN announced that they had detected a new particle.
Wow.
And it had a mass of around 125 GeV, which is exactly what the theoretical predictions for the Higgs boson suggested.
That's huge.
Yeah, it was a monumental moment in physics.
And it was a Nobel Prize shortly after, right?
It was, yeah. Peter Higgs and Francois Englert were awarded the 2013 Nobel Prize in Physics.
For their work?
Yeah, for their theoretical work.
Wow. So this wasn't just some abstract theory.
No, it was the culmination of a decades-long detective story, culminating in this incredible discovery at the LHC.
And the story isn't over, is it?
No, it's not.
Because I know our source mentioned that research is ongoing.
It is.
So does that mean that even after all this time and effort, there's still aspects of the Higgs we don't understand?
Absolutely. Scientists are still working hard to understand all of the Higgs boson's properties in detail.
Okay.
And they're also looking to see if it might offer clues to physics beyond the standard model.
Beyond the standard model.
Yeah, because the standard model, while incredibly successful, doesn't explain everything.
Okay, so you've mentioned the standard model a few times now.
Yeah.
I think for people who aren't, particle physicists like myself.
Sure.
It would be good to just kind of give an overview, like what is the standard model and where does the Higgs boson fit into all of this?
Okay, so the standard model, you can think of it as the most successful rule book we have for understanding the fundamental building blocks of the universe and how they interact with each other.
Okay.
It describes the most basic particles and 3 of the 4 fundamental forces.
Okay.
So we have the strong force, which holds the atomic nuclei together.
Okay.
We have the electromagnetic force responsible for light and electricity.
Okay.
And we have the weak force involved in radioactive decay.
Got it.
Now, importantly, gravity is not part of the standard model.
Okay, it's kind of its own thing.
No, exactly. It's a separate thing.
Okay, so what about these fundamental particles that the standard model describes?
So the standard model describes 2 main groups of particles.
Okay.
We have the fermions, which make up matter.
Okay.
And we have the bosons, which carry forces.
Got it. And so the Higgs boson is a boson, but it doesn't carry a force.
You got it. The Higgs boson is unique in that sense.
Okay.
So fermions, you can think of them as the ingredients of matter.
Okay.
They have a property called spin, which is a fundamental property of particles.
Okay.
And it's a half integer value.
Got it.
And fermions include quarks, which make up protons and neutrons.
Okay.
And leptons, which include the electron, the muon, the tau, and their neutrinos.
Okay, so those are the fermions of the matter particles.
Exactly. Now, bosons have integer spin.
Okay.
And they are the force carriers. So we have the photon,
Right.
which carries the electromagnetic force. We have gluons, which carry the strong force binding quarks together.
Okay.
We have the W and Z bosons, which are responsible for the weak force.
Okay.
And then we have the Higgs boson, which, as we said, gives mass to other particles.
Right. So the Higgs boson, it's a boson, but it doesn't actually carry a force.
Right. It has a different role.
Yeah.
It's responsible for mass.
For mass. Okay, so one of the big questions that the standard model was trying to answer was why these particles have mass in the first place, right?
Exactly. Why do particles have mass?
Yeah, like where does it come from?
Yeah, that was a fundamental question.
Right. So what's the explanation that comes with the Higgs?
Okay, so the standard model proposes that particles were originally massless.
Okay.
And they gain mass through their interaction with the Higgs field.
Okay, so it's not like they inherently have mass.
No.
They get it from somewhere.
Exactly. They get it from the Higgs field.
Okay, so is this Higgs field like localized? Is it everywhere?
It's everywhere.
It's everywhere.
The Higgs field permeates the entire universe.
So it's like this universal field that gives particles mass.
Exactly. And the way it works is that the Higgs field doesn't like to be at zero energy.
Oh.
It prefers to have a different non-zero value. And this preference is what leads to particles gaining mass.
So this preference leads to something called spontaneous electroweak symmetry breaking.
Exactly. That's a mouthful.
It is. So can you break that down for us?
Sure. So imagine you have a perfectly round table with a ball balanced in the very center.
Okay.
Now, this is perfectly symmetrical, right?
Right. Perfectly symmetrical.
But if you give it a tiny nudge, the ball will roll off to one side.
Right. It'll fall off.
And it will break the symmetry.
It breaks the symmetry.
In a similar way, the Higgs field prefers to have a non-zero value everywhere.
Okay.
And this breaks the initial symmetry of massless particles,
Okay.
causing some of them to acquire mass.
Okay, so it's this breaking of symmetry that gives them mass.
Exactly.
That's fascinating. So it's not an inherent property. It's about how they interact with this Higgs field.
Right. It's all about interaction.
And this interaction strength determines the mass.
Exactly.
Okay, so stronger interaction, heavier particle.
You got it.
Okay, so we've been talking a lot about this Higgs field, but our source is called Higgs boson.
Yes.
So what's the connection there?
So the Higgs boson is a quantum excitation of the Higgs field.
Okay, what does that mean, quantum excitation?
Okay, so imagine the Higgs field is like a calm lake.
Okay, a nice calm lake.
Yeah, and if you throw a pebble into it,
Yeah.
you create ripples.
You get some ripples.
Those ripples are the Higgs bosons.
Oh, okay.
So the Higgs boson is like a little disturbance in the Higgs field.
Okay, so it's not the field itself.
No.
It's like a disturbance in the field.
Exactly, a little excitation.
Okay, got it. So if we could actually observe a Higgs boson, what are its characteristics?
So the Higgs boson has a mass of about 125 GeV.
Okay.
It's electrically neutral, which means it doesn't have an electric charge, and it has a spin of 0.
Okay.
And it interacts with all particles that have mass.
So everything that has mass interacts with the Higgs boson.
Exactly. And the stronger the interaction, the more massive the particle is.
Okay, so heavier particles have a stronger pull towards the Higgs boson.
You got it.
Interesting. And so how do we actually detect the Higgs boson? Because our
Yeah.
source talks about these decay channels.
Yeah, so because the Higgs boson is so unstable,
Okay.
it decays very quickly into other particles.
Right.
And some of the ways it decays include transforming into two bottom quarks
Yep.
or into two photons.
Okay, so it breaks down into other things.
Yeah, and it's these decay products that we actually detect in experiments.
Okay.
So we can't see the Higgs boson directly,
Right.
but we can see what it decays into.
Got it. So we see the aftermath.
Exactly.
Okay, so let's dig a little deeper into some of its quantum mechanical properties.
Okay.
Our source says it's a boson.
Yes.
So what does that mean in terms of quantum mechanics?
So as a boson, the Higgs boson follows Bose-Einstein statistics,
Okay.
which means that multiple Higgs bosons can occupy the same quantum state.
Okay, so they don't mind being in the same state.
They don't mind at all.
Okay,
Yeah.
other particles do mind.
Yeah. So fermions, for example, are subject to the Pauli exclusion principle, which says that no two fermions can occupy the same quantum state.
Okay, so bosons are more social in a way.
Yeah, you could say that.
Okay, and what about its spin? You said it has a spin of 0.
Yeah, so spin is another fundamental property of particles.
Okay.
And the Higgs boson has a spin of 0, which distinguishes it from other force-carrying bosons.
Right, which have different spins.
Exactly.
Okay, and then the fact that it doesn't have an electric charge, that also has implications, right?
Absolutely so. Because it's electrically neutral,
Okay.
it doesn't interact directly with the electromagnetic force.
So it's not affected by electric or magnetic fields.
Exactly. It's like a ghost to those fields.
Wow, that's really interesting. So our source also mentions the theoretical possibility of its role in Bose-Einstein condensates and collective quantum phenomena.
Yeah, so because Higgs bosons are bosons,
Okay.
there's a theoretical possibility that at extremely low temperatures, a large number of them could all occupy the same quantum state,
Okay.
forming what's called a Bose-Einstein condensate.
And that's like a really unique state of matter, right?
It is, yeah. It's where quantum effects become visible at macroscopic scales.
Wow. Okay. So what about entanglement? Can Higgs bosons be entangled?
That's a tricky question because the Higgs boson has such a short lifespan.
Right. It decays really quickly.
Yeah, so it's practically impossible to entangle them before they decay.
Okay.
However, the particles that the Higgs boson decays into can be entangled.
Oh, okay. So it's like the descendants of the Higgs boson that get entangled?
Exactly.
That's fascinating. Could that have practical applications?
It could, yeah. So by studying the entangled particles that come from the decay of the Higgs boson, we can learn more about the Higgs boson itself
Oh, that's clever.
and about the fundamental forces involved.
So it's like a backdoor way of studying the Higgs.
Yeah, kinda.
Okay, so we've talked about entanglement.
Yeah.
What about quantum coherence? Can something that exists for such a short time even maintain quantum coherence?
That's a really good question, and it's a challenge for sure.
Right.
Because the Higgs boson decays so quickly. But what's interesting is that the process of its decay is still governed by quantum mechanics.
Okay.
So there's a lot we can learn from studying the decay process itself.
So even though it doesn't last very long,
Right.
there's still quantum information encoded in its decay.
Exactly.
Okay, so let's go back to how it interacts with other particles.
Okay.
We know that heavier particles interact more strongly,
Yeah.
but can you give us a little bit more detail on that?
Sure. So the strength of the interaction is proportional to the mass of the particle
Okay.
and inversely proportional to the vacuum expectation value of the Higgs field.
Okay, so heavier particles have a stronger connection to the Higgs boson.
They do.
Interesting. And you mentioned earlier this Yukawa interaction for quarks.
Yes. The Yukawa interaction describes how quarks interact with the Higgs field.
Okay, and that's what gives them their mass.
Exactly.
And I know that the LHC is still doing research on how the Higgs boson interacts with other particles like leptons.
Yeah, they're trying to make very precise measurements of those interactions.
And why is that so important?
So those measurements are important for testing the standard model.
Yep.
Because the standard model makes predictions about how those interactions should work.
Right.
And if the measurements don't match the predictions, then that could be a sign of new physics beyond the standard model.
Okay, so it's a way of looking for cracks in our current understanding.
Exactly.
Okay, and finally, let's talk about the Higgs boson's role in giving mass to the W and Z bosons,
Okay.
which is like the whole reason this whole thing started, right?
It is, yes. So the W and Z bosons are responsible for the weak force.
Okay.
And they gain their mass through the Higgs mechanism,
Huh.
the same mechanism that gives mass to other particles.
So it's all connected.
It's all connected.
Okay, so now let's move on to something that I know you, the listener, are particularly interested in,
Okay.
which is the significance of the Higgs boson for quantum technologies.
Yeah, that's where things get really interesting.
Yeah, so can we use the Higgs boson to build quantum computers?
So, unfortunately, not directly. Because the Higgs boson has such a short lifespan.
Right, it decays too quickly.
Yeah,
But the underlying physics of the Higgs boson could still be relevant for quantum technologies.
absolutely. There are some really fascinating connections.
Like what?
So one connection is between the Higgs field and quantum phase transitions.
Okay.
Quantum phase transitions are important for controlling qubits.
Which are like the building blocks of quantum computers.
Exactly. And the way the Higgs field breaks symmetry
Okay.
is similar to how quantum phase transitions can be used to manipulate quantum states.
Oh, that's interesting. So it's like the concept of symmetry breaking is relevant in both cases.
Exactly.
Okay, so that's one connection. What else?
Another possibility is that quantum computers could be used to simulate the behavior of complex quantum fields, including the Higgs field.
Okay, so we could use quantum computers to better understand the Higgs field itself.
Exactly. And that could lead to new insights that we wouldn't be able to get with classical computers.
That's really cool. And are there any other potential applications for quantum technologies?
Yeah, so there's the possibility that mechanisms similar to the Higgs mechanism could be used to improve error correction in quantum computers.
Okay.
Because error correction is a major challenge in quantum computing.
Right, because quantum states are so fragile.
Exactly. And if we could use the principles of the Higgs mechanism to create more robust qubits,
Right.
that would be a huge breakthrough.
That would be amazing. So it sounds like there's a lot of potential there.
There is.
Okay, and what about implications beyond quantum computing, like for material science?
So the Higgs mechanism has a close relative in condensed matter physics
Okay.
called the Anderson-Higgs mechanism.
Okay.
And this mechanism is relevant to superconductivity.
Superconductivity. Okay, so what's the connection?
So in superconductors, electrons form pairs called Cooper pairs.
Okay.
And these Cooper pairs can flow without any resistance.
Right, which is what makes superconductors so special.
Exactly. And the formation of these Cooper pairs can be understood through a mechanism that's similar to the Higgs mechanism.
Oh, that's fascinating. So the way the Higgs field gives mass to particles is similar to how electrons pair up in superconductors.
Yeah, there are some really deep connections there.
That's incredible. And our source mentions that scientists have observed Higgs-like excitations in certain materials.
Yes, they've observed what are called Higgs modes.
Higgs modes.
Yeah, and these are collective excitations that arise from the behavior of electrons in certain materials.
Okay, so it's like the Higgs boson, but as a material.
Kind of, yeah, it's a similar concept, but in a different context.
And could these Higgs modes lead to any technological advancements?
Potentially, yeah. So our source suggests that understanding these Higgs modes could help us develop more robust superconducting qubits.
Okay, so we could potentially use Higgs modes to create better qubits.
Exactly.
Wow, that's amazing. So beyond specific applications like computing and material science, there's also the potential impact on precision measurements and quantum sensing.
Right. So even though the Higgs boson itself might not be used as a sensor, the advancements in high-energy physics that led to its discovery have led to the development of new technologies that can be used for very precise measurements in other fields.
Okay, so it's like a spin-off effect.
Exactly.
Okay, and our source specifically mentions the potential to use the Higgs boson to determine fundamental constants of nature.
Yeah, so by measuring how the Higgs boson interacts with other particles, we can refine our understanding of those fundamental constants.
Okay, so it helps us make more precise measurements of those constants.
Exactly.
Okay, and then there's the idea of using the Higgs boson in interferometry experiments.
Right, so interferometry is a technique that uses the interference of waves to make very precise measurements.
Okay.
And if we could do interferometry experiments with Higgs bosons, that could give us new insights into the structure of the vacuum itself.
The vacuum.
Yeah, like the empty space that permeates everything.
Oh, wow. That's really pushing the boundaries.
It is.
And what about the connection to gravitational wave detection?
So gravitational waves are ripples in space-time.
Okay.
And they're incredibly difficult to detect.
Right.
And our source suggests that a better understanding of Higgs physics could indirectly contribute to the detection of gravitational waves.
Okay. So it's not that the Higgs boson itself is involved in gravitational waves.
Yeah.
But understanding the Higgs boson could help us understand gravity better.
Exactly.
Okay. So it seems like even though we might not be building quantum computers out of Higgs bosons anytime soon,
right,
the knowledge we gain from studying the Higgs boson could have a huge impact on quantum technologies.
Absolutely. It's all about the fundamental physics.
Right. And our source also points to future experiments in high-energy physics as a potential source of new discoveries.
Yeah, so experiments like the upgrades to the LHC and the proposed Future Circular Collider and the International Linear Collider.
Okay.
These experiments are designed to push the boundaries of our understanding of particle physics.
Okay.
And they might reveal new particles that could be relevant for quantum technologies.
New particles that we haven't even imagined yet.
Exactly.
And then there's the intriguing possibility of a connection between the Higgs field and dark matter.
Yeah, dark matter is one of the biggest mysteries in physics.
It really is.
And there's a possibility that the Higgs field might interact with dark matter.
Okay.
And if it does, then we might be able to detect that interaction by looking for the Higgs boson decaying into invisible particles.
Invisible particles?
Yeah, particles that we can't detect directly.
Wow, so that would be a huge discovery.
It would be.
And then finally, there's the concept of vacuum fluctuations of the Higgs field.
Yeah, so in quantum field theory, even empty space is not truly empty.
Okay.
It's filled with virtual particles that are constantly popping in and out of existence.
So it's like a seething mass of activity even in empty space.
Exactly, and the Higgs field is part of that.
Okay.
So the Higgs field is constantly fluctuating even in the vacuum.
And studying those fluctuations could give us new insights into the nature of quantum fields.
It could.
Okay, so we've covered a lot of ground here.
We have.
And it seems like the Higgs boson is much more than just a particle that gives mass to other particles.
It is, yeah. It's a really fundamental piece of the puzzle of our understanding of the universe.
Exactly. So now let's shift gears a little bit and talk about the experimental challenges of studying the Higgs boson.
Okay.
Because I imagine it's not easy to study something that exists for such a short time.
It's not easy at all.
So what are some of the main challenges?
So one of the biggest challenges is creating the Higgs boson in the first place.
Okay.
Because it requires these massive amounts of energy.
Right, we talked about that.
Yeah, and then once you've created it, it decays very quickly.
Right.
So you have to detect it very quickly.
Okay, and how do you actually detect it?
So you detect it by looking for the particles that it decays into.
Okay.
But that's also a challenge because there are lots of other particles being produced in these high energy collisions.
Right, so it's like trying to find a needle in a haystack.
Exactly. You have to be able to distinguish the signal from the noise.
And I know our source mentioned specific ways that scientists look for the Higgs boson.
Yeah, so they look for specific decay channels.
Okay.
Like the decay into two photons or the decay into two Z bosons.
Okay.
And each of these decay channels has its own unique signature.
Okay, so it's like looking for a specific fingerprint.
Exactly.
Okay, so it's clearly a huge technological challenge to even study the Higgs boson.
It is.
But beyond the technical challenges, there are also some really profound philosophical questions that come up.
Oh, yeah. Absolutely.
When you start thinking about the implications of the Higgs boson.
Yeah, it really makes you question some fundamental things about the universe.
Like what?
Like, what is mass, really?
Okay, yeah, because we tend to think of mass as just an inherent property of matter.
Right. It's just something that things have.
Yeah, but the Higgs mechanism tells us that mass is actually the result of an interaction.
Exactly. It's the result of particles interacting with the Higgs field.
So it's not something they have, it's something they do.
Yeah, it's more like a process than a property.
That's a huge shift in perspective.
It is.
And it really makes you wonder about the nature of reality itself.
Yeah, like what is matter, really?
Right. And then there's the question of why different particles have such different masses.
Yeah. The standard model doesn't explain that.
So we still don't know why some particles are heavier than others.
We don't know why the Yukawa couplings have the values they do.
Right. So there's still a lot we don't understand about mass.
There is.
And the Higgs boson might be the key to unlocking those mysteries.
It might be.
And speaking of mysteries, the Higgs boson could also play a role in our search for a more complete theory of the universe.
Yeah, a theory that goes beyond the standard model.
Right, like a theory of everything.
Exactly, a theory that unifies all the forces, including gravity.
And the Higgs boson could be a bridge to that theory.
It could be because it's connected to all the other particles.
Right, and our source even mentions the possibility of other Higgs bosons.
Yeah, some theories predict that there might be multiple Higgs bosons.
Multiple Higgs bosons? Wow. And what about the idea that the Higgs boson itself might not be a fundamental particle?
Yeah, some physicists think that the Higgs boson might actually be made up of even smaller particles.
So there could be a whole other layer of substructure that we haven't even discovered yet.
Exactly.
And then there's the big question of how the Higgs field relates to gravity.
Yeah, that's the holy grail of physics.
Trying to unify quantum mechanics and general relativity.
It's the biggest challenge we face.
And the Higgs field could be a piece of that puzzle.
It could be.
Because it's a fundamental field that permeates all of space.
Right, and it could have connections to the structure of space-time itself.
Okay, so we've covered a lot of really mind-blowing stuff today.
We have.
And it's clear that the Higgs boson is much more than just a particle that gives mass to other particles.
It's a fundamental component of our understanding of the universe.
Exactly, and it might hold the key to some of the biggest mysteries in physics.
It might.
So as we wrap up this deep dive, let's summarize the key takeaways for you, our listener.
Okay, so the Higgs boson is responsible for giving mass to other particles.
Okay.
It does this through its interaction with the Higgs field.
Okay.
And the discovery of the Higgs boson was a monumental achievement in physics.
It really was.
And it opened up new avenues for research.
Right. And even though the Higgs boson itself might not be directly used in quantum technologies anytime soon,
right,
the underlying physics of the Higgs boson could have a profound impact on the future of those technologies.
Absolutely.
So here's a final thought for you to ponder.
Okay.
Could our understanding of this seemingly ephemeral particle, the Higgs boson, ultimately unlock even deeper secrets about the universe?
It's a very intriguing possibility.
It is. It really makes you think.
It does.
You know, this particle that's responsible for something as basic as mass.
Right.
It makes you wonder what other fundamental truths are out there waiting to be discovered.
Absolutely. There's still so much we don't know.
Exactly. So keep those questions coming, and we'll keep digging deeper into the mysteries of the universe.
We will.
Thanks for listening.
Thanks.